So this one is technically called change of variables, but the way that I did the last one is I didn't choose f of x and g of x, I just used u right away. So this is essentially the same thing we just did, so it's the second part of the video, doing the exact same thing that I just did in the last one. So I'm still going to use u and du rather than g of x and f of x and whatever and make a composition of functions. To me, u prime, or finding the derivative of u and using u, just makes a heck of a lot more sense. So again, using change of variables for this guy is exactly what I would have done before, but you're going to see me write it just a little bit differently, but it's really the same idea. So just as I would before, I would take this inner guy and call it u. So u is 2x minus 1. So this is the part that you might see look a little bit different, which I probably didn't make clear on the last one. So if I'm taking the derivative of u with respect to x, so the derivative of this guy with respect to x is 2, which means that dx is du over 2. So why does that matter? Well, because remember on the very last example we just did, we ended up with pattern recognition almost. So it almost made sense, but not quite, and we had to then take it times 2 on the inside and times a half on the outside. So doing it in this way basically makes it so I don't have to worry about that. So here I'm saying that dx is equal to du divided by 2. So if I'm replacing this with u's, this is u to the 1/2, and then dx is being replaced by du over 2. And the du over 2, magically, because it's dividing by 2, turns into a 1/2 on the outside. So it's the exact same thing. On the last one, I had to actually think about it. What would I have to multiply by to make it fit the pattern? On this one, we're saying you don't have to worry about it because we've already changed the variables, so just plug things in directly. So whichever one makes more sense to you is what you should do. So now I have 1/2 times the integral of u to the 1/2 du. Pretty straightforward from here. U to the 3/2 divided by 3/2, I still have the 1/2 on the outside. Don't forget plus c. Do some simplification, so this actually ends up into 2/3 times. So I end up with 1/3 on the outside, u to the 3/2, and then of course I replace the u with 2x minus 1. So as you'll notice, this looks almost exactly the same as I did with pattern recognition, except for this step right here, which is essentially I don't have to think as much, I just have to do a little bit more substitution, or substitution in a different way. So again, here's the guidelines. Choose your function to be u, find the derivative of that, write the integral in terms of u, write the resulting integral in terms of u, plug the function back in for u, and check your answer by differentiating. And most of the time I'm too lazy to do that one, but feel free. If that's a quiz or a test, baby, you integrate it or differentiate and make sure it works out. So again, let's take a look at this question together. Using change of variables, I would still start by saying u is 2x plus 3, and then derivative of u with respect to x would be 2, which means that dx is going to be 2 divided by, or sorry, du divided by 2. So now I'm just going to plug stuff back in. Here's my original function. I'm going to say this is 6 times u squared times du over 2. Well, the 6 and the divided by 2 turns into a 3, and I popped that guy to the outside. So that just gives me u squared du. Very easy to integrate that. So it's u cubed divided by 3. I've got the 3 on the outside still. Those end up canceling each other out. So I just get u cubed plus c, then take u and plug it back in. So again, same exact thing we did with pattern recognition, except for this step right here where I'm very deliberate about finding du over dx and then turning it into in terms of dx so that I can plug it directly in instead of having to worry about making it fit the pattern. Practice makes perfect, so we're just going to keep practicing because this is an acquired skill that you can get better at. So again, what would I do here? I would say u is x squared plus 3, which means derivative of u with respect to x is 2x, which means that dx is equal to du divided by 2x. So now let's take a look. How is this going to work? Here's my original integral. I'm replacing replacing x squared plus 3 with u and calling it u squared. I'm replacing dx with du over 2x. Notice I didn't do anything with 4x yet. So now I'm going to reduce and say, well, the x's go away and the 4 over 2 reduces to 2 and 1, which gives me this integral. From here, it's very straightforward. Keep the 2 on the outside, integrate u squared to get u cubed over 3, do some simplification still with u. When we get to the end, plug in the function for u back in for u. I've tried to include as many difficult or different examples as I could, so this one is different or more difficult because we have an extra x. So here's what I mean by that. If I find u is 2x minus 1. Then if I take the derivative of u with respect to x, that gives me just 2, which means dx is equal to du divided by 2. So if I were to rewrite this, I have the integral of x, and then u to the 1/2, and then instead of dx, I have du over 2. And notice, on the last example, I ended up with an x here, but then I had an x down here, and those guys canceled, and that's not what I have now. So let's take a look at how we deal with that. How I deal with that, I'm going to move that out of the way so it's not in your way. How I deal with that is I'm going to take this guy and I'm going to manipulate it and say if u is 2x minus 1, then u plus 1 is 2x, and u plus 1 divided by 2, plus 1 divided by 2 is equal to x. So I'm going to have to end up substituting that as well. So again, just like I showed you before, I can integrate the u plus 1 over 2, and then u to the 1/2, because this was x, u plus 1 over 2. 2x minus 1 is u to the 1/2, and then dx turns into du over 2, and then I just have to do some, distributive property and all of that fun stuff. So I end up with 1/4 u to the 3/2 plus u to the 1/2 du. Now I can do my integration. So if I have 3/2, I'm going to add 1 to that, so 5/2 over 5/2, and then 3/2 over 3/2, that turns into this guy. Keep doing your math and algebra, reduce by multiplying by 1/4, and that gives me this guy. Once I'm to this point, then you plug the u back in, and this is my final answer. So again, the tricky part here was we did our normal steps at the beginning, but then we had an extra x, and we can't integrate when we have two variables inside the integral. So I had to rewrite this so that I could also replace x with u plus 1 over 2. So let's kick things up a notch and find the equation whose derivative is f of x equals cosine of x over 2 and passes through the point 0, 3. So how is this going to change it? Well, up to this point, we have just found the general solution. So we had the plus 3. So really, the first whole part down to my purple line is going to be exactly the same as we would normally do. I would call u x over 2. Then I would find du over dx is 1/2, which means dx is 2 du. I would do that direct substitution using change of variables and move the constant to the outside. So really I'm integrating cosine of u du, and up to this point then, obviously when I integrate cosine I get sine. So I have 2 sine of u plus c, which when I reintroduce what u was equal to, x over 2, I get 2 sine of x over 2 plus c. So if they just said, find the antiderivative, I'm done. So that is f of x. That's my original function. Then it says it passes through the point 0, 3. So essentially I am finding my not general solution, but particular solution. So I'm taking this guy, 2 sine of x over 2 plus c. I'm plugging in 0 for x, and I'm setting it equal to 3 for y, and I'm solving. And when I solve that, I took sine of 0, which was 0, times 2, which was 0, plus c. So c happened to be 3. So my final answer, my particular solution, almost the same as what I did here, but this is with a c. Then I just took it to the next step and plugged in the point 0, 3. All right, let's take a look at another example. This is one for you to try on your own. So if you would press pause, try this question, then press play to see how you did. So again, I'm asking for an equation, but I want you to do it the same way that you did it before. The only part that's going to be different is when you get to the end, you're going to find the particular solution instead of plus c. So how I would start is I would call this guy u, then I would find the derivative of u with respect to x, which is 2x, and then change it into dx equals du over 2x. I need it to all fit into my little pattern, so notice I've replaced not the 2x, but I've replaced the u and the dx with my other functions, and then it turns out 2x cancels, which is fantastic. So I'm finding the integral of u squared du, which is of course u cubed over 3 plus c. So my final answer, if they asked for just the general solution, would be right there. I would be done. Because they then asked me to find the actual equation through the point 0, 3, I now have to take this to the next level, and instead of x, I'm plugging in 0, and instead of well, not instead of anything, equal to the y value, which is 3, since that's an equation or a function. So that's what I did here. I took all of this, plugging in the 0 for x, plus c equals 3. I did the math to find that c was negative 6. I didn't show all of that work, but I feel confident that you can probably work that out yourself. And so my final answer, which is the equation of the derivative, is x squared plus 3 quantity cubed divided by 3 minus 6. So we're going to finish out this week by talking about change of variables for definite integrals. And you'll notice that it's really the same thing that we did before, except the one caveat or the one trick here is sometimes we're going to have to go to changing the limits of integration. Because if I change everything over to u, oftentimes it's easier to change the limits of integration. Or the other method is, of course, to go ahead and turn everything into u, do all of the work, and then turn it back into x and use the original limit. So I'm going to show you what I mean by all of that hubbub. Here's an example. And again, so far we've just been doing this with indefinite integrals, so it was the plus c, but now I've got limits of integration, 0 and 1. But I'm still going to start the same way, so I'm still going to start by saying let's let u be x squared plus 1. Let's let the derivative of u with respect to x be 2x, which means that dx is du divided by 2x. So that's what I do first. Then I'm going to start replacing things. This guy is u cubed. I kept my x out front because I haven't done anything with it yet. And then I've replaced dx with du divided by 2x. Then I did whatever simplification I could, so that included getting rid of the x's here, and then taking this 2 and saying let's move it to the outside, so it's 1/2 on the outside. On the inside, I just have u cubed du, which I can integrate very easily. But now, here's the trick. Originally, I'm going to get rid of all of my markings. Originally, I was going from 0 to 1. And notice when I came down here, I magically shifted from 1 to 2. Now, how did I do that? Well, let's take a look at the math that I skipped over on purpose just to make sure we understood what we were doing. So if I had 0 to 1, what I can do is I can say, well, when x is 0, let's find out what u is. So my original limit was 0. That was my lower limit. So now if I take u and plug in 0, I get 1. So now my new lower limit with respect to u is 1. So because I'm rewriting everything with respect to u, it makes sense that I would change that limit. Then, because my former upper limit was 1, I'm just going to take 1 and plug it in for my u function and find that my upper limit is 2. So that's why I'm integrating from 1 to 2. I didn't just arbitrarily pick those numbers 1 and 2. The reason that I like this way better is if I didn't do it this way, then I would have to integrate, and I would have to replace u back with x squared plus 1, and then I would have to integrate using 0 to 1. So really it's the same thing. So this would let's just make things confusing. If I had 1/2 and then u to the 4th turned into u, which is x squared plus 1 to the 4th over 4 from 0 to 1, let's see what happens here. Because as we can see, I've already worked it out for plugging in 1 and 2 with u. But if I went back to the x's, let's look at that. So if I plugged in 1, that would be 1 squared plus 1, which is 2 to the 4th. 2 to the 4th is 16 divided by 4, so it's 1/2 times 4 minus 1/2 times, if I plug in 0, 0 plus 1 is 1, 1 to the 4th is 1, so that's 1/4. And so I end up with 1/2 of 4, which is 2, minus 1/2 of a 4th, which is 8, which gives me, guess what, 15/8. So as we can see, I can, at this point, instead of doing this extra step, which is integrating with new limits of integration, I can take this, turn it back into x, and use my original limits of integration. So when it comes to u, you decide which way makes the most sense to you. But what I don't want you to do is I don't want you to take u to the 4th over 4 and plug in 0 and 1, because that's going to give you a wrong answer. So again, you make that decision whether or not you're going to change the limits, or if you're going to go to u, back to x, and then use the original limits of integration. Two more examples for us to go through together. Again, as always, you cannot watch every example. If you feel like there's too many examples, I would rather put in too many than too few. So again, taking a look at this one, I would call u 3x squared plus 2, find the derivative of that, so that now I can replace this with u, I can replace this from dx. So using my original here, I'm going to say 3x, u to the 1/2, and then du over 6x. Just as I was hoping, these guys canceled. The x's did. The 3 over 6 turned into the 1/2, and I just end up with u to the 1/2 du. So again, I went ahead and changed my limits of integration. Notice I started at 1 and 3. To find my new limits of integration, I just plug 1 into my u function, and I plug 3 into my u function. So I got 5 and 29. So notice that's what I'm using here, 5 and 29. From here, it's real straightforward. 1/2, u to the 1/2 is u to the 3/2 divided by 3/2, or 2/3 u to the 3/2. These guys cancel, and now I'm plugging in 29, and I'm plugging in 5. So again, using those new limits of integration helps me to find the answer more easily. And when I'm done, I end up with 48.3298. Hey, last one, best one. I used to have a fitness instructor who said that. It really drove me nuts. So hopefully it drives you nuts too. Last one, best one. We are going to do a tricky question. So to start this question, of course, I would start it, as always, by saying u equals x squared plus 3. And then du with respect to x would be 2x, which means what I would really be looking for is dx is equal to du divided by 2x. And if I started to rewrite this, this would be the integral from 0 to 4, well, not from 0 to 4, we can find those in a minute, of u to the second and then du over 2x. So why am I concerned about this? Is something different than normal? Yes, because typically I'm going to have an x here that cancels with the x with my other du function. So how am I going to go around this? We have to FOIL. Oh my gosh, I know how much you love that. So let's FOIL it out. Let's take x squared plus 3 and FOIL it out. That means x squared plus 3, x squared plus 3. Multiply those terms, I get x to the fourth plus 3x squared plus 3x squared plus 9. Now what? I'm not going to use this at all. I'm not going to use any substitution. I'm just going to directly integrate this. Each particular term I'm going to integrate. So x to the fifth divided by 5 plus 2x cubed plus 9x. Again from 0 to 4 because I didn't change anything. I didn't use u substitution on this question at all. So now I just plugged in the 4, I plugged in the 0, and I subtracted. Great job. I know this was a long video, but it's because I included a whopping 10 examples for us to try.